the electric field is the negative gradient of the potential. Now, if I put a negative charge here, which way would it go? If I put there was a hand gesture on that one, so in case you miss it, since I guess no one can actually see her except for me. This way. If I put a positive charge here, which way would it go? Which way would it be forced? All right, got a lot of gestures from the back of the room. They're all in agreement for those. There we go, some front of the room. That's going to be forced that way, that's going to be forced this way. So in general, a negative charge is going to move to a higher potential. A positive charge moves to a lower potential. Unlike potential energy, where both charges would want to move to a lower potential energy, in terms of potential, the electric potential, not the energy bit, negative charges want to move to a higher potential, positive charges want to move to a lower potential. So we now have our fourth explanation. I know a positive charge produces, as you move away from it, a decreasing electric potential. A negative charge would produce, as you get farther away, an increasing electric potential. Because if that were negative 4 nanocoulombs, that'd be negative 36, negative 18, negative 12, negative 9. We are increasing in potential. Negative charges placed in amongst the electric potentials has a desire to move to a higher potential. Positive charges want to move to a lower potential. Four explanations for the exact same thing. And it's going to turn out that as we get farther on, we're going to be dealing with this less and less, and this more and more. So the physics 151 approach, physics 152 approach. And also note, we've had one physics equation. This is the only physics equation we've done. The rest of it is definitions and math. It'll be another month or so before we get to our second physics equation. All right, 151, there was 3 physics equations. F equals ma, generalized gravitational force, and Hooke's law. I think that was it. The rest were just math and definitions. Questions before I make this disappear? I still haven't talked about voltage. Let's talk about voltage. All right, so I've got this potential set up, these actual potential lines set up. I'm going to take an object. I have a particle here, starting at the 18. It is going to move. I've got some sort of bizarre setup going on, and it moves from here to here. I guess it's not that bizarre. What is the change in the electric potential that this particle experiences?
What was the question?
I have a particle that moves from the 18 volts to the 12 volts. What is the change in the electric potential?
6 volts? Is that what you're asking?
Sort of, yeah, that's not quite the right answer. But yeah, that's the kind of thing. I know how you got that, but you missed something.
Negative 6 volts?
There we go. Final minus initials, 12 minus 18. So the change in my electric potential for this particle is negative 6 volts. All right, so I'm going to start from here. I'm going to go there. I'm going to go to the 9. What is my change now?
Negative 9 volts.
All right, we're cruising. Questions here before I make it look more bizarre? I am now going to start here. And this time the particle, because of some bizarre configuration, is going to go do some circles here. And yes, the particle does come inside this charge briefly. What is the change in the potential?
Negative 6 volts.
Yeah, so the path it takes doesn't really matter. It's just where I ended up minus where I started. So if I'm talking about the change in electric potential, all I care about is beginning and end. Because of the constant, remember, we could have set the potential here to be 0, in which case the potential here would be negative 18, negative 6, negative 18, let's subtract 36 from all of it, negative 24, negative 27. It doesn't change the difference in the potential. Adding the constant will just change all of these equally. So this difference in potential, I can just call it the change in potential, which, and I'll put electric in parentheses here. Given the context, the potential would be electric. Change in electric potential, or electric potential difference, and typically you would see it as electric potential difference or potential difference instead of change in electric potential. Why? Just have it. And it does have one other name, one other thing I could call the exact same thing, and that is voltage. Voltage is the potential difference. Now we do run into the same thing that we've run into before about when you use displacement and position interchangeably. There are a number of things like that. Actually, when can displacement and position be used interchangeably? The flashback 6 months or a year and 6 months.
What was the question?
When can displacement and position be used interchangeably? You have an answer? I think that was a maybe. I don't have the hearing aid yet. Laura's looking at you to give the answer to say. Do you want to whisper it to Abby and have her tell me?
I don't know what I was gonna say now.
Okay. Position, displacement.
Yes. I mean, I remember that, but I don't know how to answer the question. I don't know what answer you're looking for. Is it like when? I don't know when there's a change in position?
When is the change in position and the position the same?
When it hasn't moved.
Not necessarily.
At the starting point.
Pardon?
At the starting point?
No. But you had a key word there. What is position?
Yeah.
the starting point.
Not the starting point, not necessarily.
Any point.
Where it is in that moment?
With respect to what?
With respect to its initial,
That's this one.
okay.
Displacement is where an object is, overall displacement, where an object is with respect to its starting point.
Oh, the origin.
Yes,
Where-
position is where an object is with respect to the origin. So when can these be used interchangeably?
At the origin.
When the starting point is the origin?
There we go. All right,
There we go.
remember the thinking
Good
that
thing I didn't say
Thank you.
my displacement would be my final position minus my initial position. If my initial position is 0, then this is just gonna be, my displacement is just my final position, or otherwise known as the position. We do this, some textbooks will do the same thing over there. Let's not lose track of this is Physics 152, not just a 151 review. So over there, I know that my voltage is the change in my electric potential, which is the final minus my initial. No vector symbols, despite my impulse to do it just then. Because of that constant, I can set 0 anywhere I want it to be. Similar to here, I can set my origin anywhere I want it to be. Here, I can set 0 potential anywhere I want it to be. So if I set that equal to 0, then I'm left with my change in potential is just equal to my potential. And some textbooks do that, and so you will see some difference in notation. I think your textbook does it. I've had other 152 textbooks that don't do that, and they do differentiate. So later on, we will get the formula delta V equals IR. Don't worry, we're gonna derive it, and also it brings in 2 letters we haven't used yet. Some textbooks will just write V equals IR. This is proper. This makes an assumption. This assumes that you're setting your electric potential 0 at some common spot, at some spot of their choosing. So suppose I've got a 12-volt battery. And I know 12-volt batteries typically don't shape like that. This is the positive side, that's the negative side. What is the electric potential at the top? Okay, anyone else? What is that 12 volts anyway? Because we have electric potential, which is in volts, and voltage, which is the change in electric potential, would also be in volts. I have 12 volts here. Is this electric potential or voltage?
It's both. Or it's the potential to have 12 volts.
If it is both, then what assumption did you make?
I don't know.
The electric potential at 0
Where?
at
The top.
the top.
If this is 0, then that is 12 volts. However, that's not necessarily an assumption that you should make. If this is 100 volts down here, what is this up here? Say it again?
112 volts.
Yeah. This, when you look at a battery and it gives you 12 volts, that is actually telling you a voltage. It is telling you the potential difference between the positive and the negative. I have no idea what the potential is at either spot. All I know is that this is 12 volts more than this. Or, flip it around, this is 12 volts less than that. Because this could be 0 volts, and this could be negative 12 volts. That's supposed to be a negative 12, my hand got sloppy there. Not that. All I know is that the positive side is 12 more than the bottom side. Questions here?
You will never know.
Yeah, you'll never, well, since you can set the potential to be 0 wherever you want, but it's gonna turn out that it doesn't matter.
Okay.
All right, here we go. We're gonna actually use some of this stuff that we've learned. If I take an infinitely charged plate, that's not the symbol I wanted to use, with a surface charge density equal to sigma. What is the electric field here? I can't tilt it. So I just have a plane of charge here. It's a plane, so this is a side view of it, and I am right here. And the question is, what is the electric field at this point? And we use Gauss's law to derive it. Pretty sure we use Gauss's law to derive it. You look like you were about to say something, Abby. Right. That's a sigma if you were trying to think of what the word was.
No.
Infinite plane of charge.
Would be the phi equals.
That's the electric flux.
Is it the sigma divided by 2 epsilon sigma?
That's the one, right there. My electric field here, the strength of my electric field is sigma over 2 epsilon sub 0. Assuming that there's nothing in the space in between the electric field lines. What about over here? What would the electric field over here be?
The same.
Drop the last part.
The same thing.
Yes. The electric field strength over here, sorry, not 2, sigma over 2 epsilon sigma. So what I'm going to do now is, we've got one plate there. So what I'm going to do is I'm going to take a plate here of some charge Q. I know that the electric field lines go away from positive. It doesn't matter where I am. We talked about last time of the symmetry, so that there's, if this is infinitely large, then my electric field lines have to be going straight away from it. And the magnitude is whatever the charge is there, sigma over 2 epsilon some naught. This over here is sigma over 2 epsilon some naught. is add a second plate. And now add another plate over here. Actually, let me extend the yellow lines. And let's give this a charge of negative Q. Or probably more properly, it should be sigma and negative sigma and sigma. Since they're infinitely large, we're about to leak into when is this an appropriate approximation, in which case there will be a charge on it. It won't be infinitely large. So from this right here, what's the strength of the electric field at this point in the middle? The electric field strength here because of this negative sigma charge distribution. The electric field strength.
Yeah, it would be negative. It would just be the same equation but negative, right?
So close. What do I mean by electric field strength? Yes. Therefore,
So it's just the same.
it's just the same, yeah.
'Cause-
Except it's a negative charge, so it's going towards it. So I've got this electric field coming towards it. And its strength is sigma over 2 epsilon sub naught. Over here, sigma over 2 epsilon sub naught. So what I have are these two infinitely large plates. They both are, they are charged. One is negative, one is positive. They have the same magnitude of charge distribution, or if these were finite plates, same magnitude of charge, just opposite signs. In the middle here, I have sigma over 2 epsilon sub naught, both heading to the right in my drawing. So the total electric field would just be the sum of those. Well, that's going to be true everywhere, but in this case, I'm going to add these two together, and I have sigma over epsilon sub